We ready? Okay, I think we're mostly ready. In today's lesson, we're going to extend our understanding of this sort of family of functions from reciprocal functions to a more general look at what we call rational functions. So that's where we're headed. But before we get there, I want to have a look at our homework and unpack it. So everyone get their homework out, please, so it's in front of them. As I stare around the room to look at where the uncomfortable glances are. Yes, Rosie. Right, okay. Sorry, Ansel? No. He has the same reason. He didn't realise there was homework. But he doesn't have... But yours is an excuse, i.e., fair enough, you weren't here. Whereas Ansel's is, how do we put it nicely? He doesn't even plead for mercy these days. He just says, you know, this is who I am. Accept me. Get out! Yeah. Normally I'd tell students to get out so we can talk about you behind your back, but I think we're all comfortable to talk about Ansel while he's still here. Yeah. Okay, so Ansel and Rosie, just follow through as you go along. But yeah, do your homework. Page 7,000, no, page 149. Question 3. Okay. The attrition rate is significant. So far I've got 4 8, which I think I can simplify down to carry the 3. A half of the students have completed it. You don't know how much? No, that is not a convincing nod in any way, shape or form. Revising. Less than half of... Zoe, have you done the homework?
It's literally just so...
Did you genuinely attempt the homework? Thank you.
I attempted it twice.
A quarter of the class. No, I prefer the more colourful statistic of 3/4 of the class didn't even look at it. You've got an excuse. You're fine. You're still in my good books. The rest of you, no supper tomorrow. No morning tea tomorrow. That's the punishment. Rosie, I'll bring you a little cupcake. Yeah. And Jeremy and Sophie, you get little cupcakes each. Everyone else, I'm not sending you to your room because that would not be a punishment, but no food for you guys. I will bring a cupcake for the 3 of you. That's it. I'm sorry, are you talking? If you bring them into class, I will confiscate them and then eat them in front of you. Do not make cupcakes, lace them with laxatives, bring them in and expect that I'll actually eat them because I know what goes on. Okay. No, let's move on. Oh, so I can't make you laugh? Okay. All right. No worries. Okay. So page 140. It's really hard. Page 149. Let's briefly look at. I'm just going to read it out loud just for the video, really, but I can't be bothered writing it down. So when lightning strikes, the light reaches your eyes virtually instantaneously, but the sound of the thunder travels at approximately 331 meters per second. However, sound waves are affected by the temperature of the surrounding air. That's interesting. The time sound takes to travel 1 kilometer is modeled by that function. I'll write it down now. So we have t for time, I think. No, yep, t for time is equal to 1,000 all over 0.6 C, where C stands for the temperature in degrees Celsius, plus 331. You're asked to sketch the graph and then what's happening 1 kilometer away. And 3 seconds before you hear anything. So we'll unpack that one as well. I'm just going to close the door because a bit of noise coming in. Okay, so honestly, all you have to do according to the textbook is really just sketch. In part A, it says sketch from minus 20 degrees Celsius to 40 degrees Celsius. So in this instance, you really just have to have a knowledge of what graphs kind of look like, reciprocal function graphs look like, and then just look at the endpoints. But that's not good enough, I think. It's a bit difficult to work out exactly what is happening. So I think for the purposes of what we're doing today, I'll unpack it a little bit more precisely for us. Even though the numbers are so big, it's going to be really a bit weird looking when I've finished. So when you're asked to graph a rational function, or in this case, a transformed reciprocal function, you have to consider the key elements of this graph. You know it's a reciprocal function, so you know that the graph is going to be something like that, right? I've got it up on the screen now. So you know it's going to be, I mean, it might be reflected, it'll be stretched, it might be shifted up or down, but, you know, it's basically going to be this shape. So we need to determine where it sits on the axes effectively. So to do that, for a rational function, we need to consider the vertical asymptote and the what did I just say? Yeah, and the horizontal asymptote. I couldn't remember which one I just said. So the first thing is the horizontal asymptote. If you remember, will be one of these kinds of lines, and it could be up that way or down that way. By default, it's along the x-axis, isn't it? Okay, so when we look at this function here, what we see is a function with no vertical shift, right? Because although the horizontal asymptote gives an implication that perhaps we're looking at the x values, we're not, because the horizontal asymptote goes up or down. But there is, in fact, no horizontal shift, okay? So therefore, the horizontal asymptote stays where it is on the parent graph. So it stays on the x-axis. Does that make sense? It doesn't move because there's no vertical shift. I'm just trying to relate it back to your understanding of how functions and transformations work, really. Now, the vertical asymptote, so I can start off with a solution here. And just like we did with quadratic functions, we are looking at critical points or critical aspects, I guess. So the first thing to work out is the horizontal asymptote, which I'm just going to use h.a. for, and that's not changing. It's y equals 0. Good, good, good. Well, what about the other one? The vertical asymptote, by default, so it's this line here, if you remember, and that is affected by a shift going left or right. And the question is there a shift to the left or right? And there is, because it's affected by this value here, right? It is to the left. Yep. One other thing that also affects it, though, which we haven't really discussed in great depth, but this will also affect it as well, because it basically it squishes the input, that 0.6. Okay, so both of these things will affect where the vertical asymptote belongs. So and the 0.6, yeah. Well, what's the relationship? This is how we work that out. The relationship for the vertical asymptote what makes a vertical asymptote is that it's effectively the impossible value of this function, right? It's t equals an impossible value. And the impossible value is found by looking at the denominator and saying, well, when will that denominator get to 0? So in a sense, what we do, I wouldn't normally write it so formally. I would say let d equal 0, and then we're going to solve for c. Okay, so we go d for denominator, right? 0.6c plus 331 is equal to 0. Subtract 331 from both sides, and we get negative 331. And then divide both sides by, oh my gosh, 0.6. And I'll need my calculator for that. And I'm just bringing up my calculator on my iPad here. So I've got negative 331. I'm dividing by 0.6. What are our expectations, guys? Is it going to be bigger than 331 or smaller? Bigger. Yeah. If you divide by a fraction, you're going to get a bigger one. D for denominator. Okay, because if you've got less than 1, then you're going to be able to fit more than, you're going to fit heaps into 331, aren't you? I mean, if it was a half, you'd be able to fit in 2 for everything. Doesn't matter. Okay, so negative 500 on your calculator, you would get negative 551. And I'm going to write it exactly because I can, 0.6 recurring. So put a little dot above the 6. On my calculator, of course, it said 666666667, but I could infer from that it would be 0.6 recurring. Sophie, question?
Negative. I was on the right track.
Awesome. Awesome. Yeah. So that gives us our vertical asymptotes. Now, the problem I have here, I can see right now that my asymptotes here, negative 551, and to a lesser extent, the horizontal asymptote of y equals 0, these are pretty big numbers, right? I also know from the textbook that they're asking me to look at temperatures between negative 20 and 40. Now, if this is the temperature where the vertical asymptote is, when I draw my graph, it's going to be quite big. That's okay, but we just need to keep in mind that it's going to be a rather stretched kind of looking graph. It doesn't ask you, to be honest, to be perfectly honest, because the vertical asymptote is all the way down at negative 551 degrees, we can in fact infer from that our graph should not have an asymptote at all over the domain that we've been asked to look at, which is, yeah, that's that. Because we're told that C represents the temperature in degrees Celsius. So technically, even though I'm going to do it because I want for completeness sake, that is beyond the domain. And so we technically don't need to draw it at all. Okay? But we're going to. What else do we need to conclude? Well, if the vertical, so at the moment, we've got something like this. We might as well just draw what we've got. So I'm going down to slide, oh, sorry, I'll just keep it zoomed out so you can see everything. So I'm going down to slide 3 now. So I've got an x-axis, sorry, y-axis, and an x-axis. So there, well, it's, to be fair enough, it's a c-axis and it's a t-axis, really. Now, the horizontal asymptote is at 0. And the vertical asymptote is at negative 551.6 recurring. So I'm just going to pop that all the way over to the side here. So I know that technically, and I'm going to draw it in red just so we can sort of see it. I know that technically, because it doesn't reflect, because we don't have any negatives there, that the graph is going to be something along the lines of that, and then something along the lines of that. Yeah? Yeah, we can do. But just again, keep in mind that when I draw this graph, I've been asked to look at the domain between negative 20 and 40. And I'm going to zoom up now so you can see it. You know, if that's the graph, if that's negative 551 here, oh my giddy aunt, negative 20 is going to be like here. And 40 is going to be like here, right? When you see the graph at the back of the textbook, you'll see that they don't even bother drawing any of this stuff here. They just draw this little bit, right, and zoom up on it effectively. So I'm really doing it for a sense of completion. I'm hoping I'm making that really clear.
We do in drawings, we take a little cutout and then you zoom it out and then you show another graph with that cutout bit.
Yeah, it wouldn't hurt actually, Jeremy. I like that idea. This gives us, but the reason why I've done it is because, in fact, you know what we might do? We might have a look at the answer in the back of the textbook now. We've got plenty more work to do on this, but it's probably worth looking at what the answer looks like in the back of the textbook. Ambrosia.
How do we know when that vertical dotted line asymptote?
The horizontal one or the vertical one? We just worked it out, Ambrosia, yeah? So if you look at slide 2 there, the vertical asymptote, by its very definition, is where the denominator is equal to 0. Okay, because as C changes, as the denominator gets smaller and smaller and smaller, and I'll just, for the sake of the video, yeah, so as C changes, in this case, it gets negative and bigger, and so it approaches negative 551. The denominator is getting bigger, is getting smaller and smaller and smaller, and so the value of t is getting bigger and bigger and bigger, because the smaller the denominator is, the bigger the number is, right? So it's getting smaller, and so t is getting bigger and bigger and bigger and bigger, which is this why it sort of arcs up like this. But the denominator cannot be equal to 0, because if it was equal to 0, then we'd be dividing by 0, and if we divide by 0, it's impossible. Yeah, they do a bit. Sorry? Yeah, I'll unpack it in a moment, yeah? I'm just trying to make sure everyone's okay with why we set d equal to 0. It's not magic. It's because just before 0, the denominator is like 0.00000000001, right? At that point, when the denominator is 0.000000001, then 1000 over 0.0000001 is a really big number. Okay, and that's represented by t being a really big number up here somewhere. And as we make the denominator even smaller, t is even bigger again. So we can see there's a trend for, as the denominator reaches 0, this graph keeps on skyrocketing upwards. Okay, t keeps on getting bigger. But we can't divide by 0, which means that at whatever the denominator is equaling 0, we have a vertical asymptote. That's where it comes from. Archie?
Is there a reason to do y-intercept?
Yes, because I haven't got to it yet. It's exactly, yeah, good question, Archie. You should always work out the critical points. I haven't done that yet because I wanted to sort of link what we're seeing with the graph. So it's not literally linear. So zoomed up, right? Sorry, what question? Was it 5C? It's gone too far. 5C, question 3. 5C, question 3. There. Okay. So if you look at the graph from the answer in the textbook, you'll see it's fair enough to say, oh, it's a straight line, but it's not. It is just a small segment of a rather large curve, which is what Jeremy was saying a second ago about. Yeah, it's why people thought the Earth was flat, right? Because the sphere is so large, it looks like it's flat from where. Oh my gosh.
It's a serious issue.
Okay. I didn't mean to bring up flat earthers frothing at the mouth there. Ambrosia.
Enlarge
Yes, that's exactly right. Ambrosia raised an excellent point there, didn't she, Ansel? Didn't she, Archie? Yes, she did. It was a really good point, and I'm so pleased that you contributed and listened to your fellow students in the classroom so that you could also share in her insightful comments, which I'm not going to repeat, and nor is Ambrosia. Oh my gosh. Yeah, you did. You'll have to watch the video now. Okay, so although it looks like a straight line, if I now switch back to this, and I might just zoom in so we can sort of get a sense of it, we can see that the answer in the back of the textbook is really just focusing on this little bit of this big long curve. Yeah, and if I zoom, I can't zoom in anymore, actually it doesn't zoom anymore, but you can sort of see why you might think it's a straight line. And I just wanted to emphasize that the reason why I've gone to the trouble of doing all this, even though it's unnecessary, is so that you can see how that little sliver of a graph fits in with the big graph. Am I making sense? Okay, so Archie asked a good question, and that was, why didn't you do the y-intercept? Are you a failure as a teacher? Now, I thought that was a bit rude when you said that, but nevertheless, we are going to move forward with looking at the y-intercept. Should we do the x-intercepts as well, or leave them? Sophie wants to.
Do we need to know what
Is there any? No, there isn't any, but I still want to, like, do I have to do anything? Because even though I know from looking at it that there aren't any, do I still have to show by domain and range?
Sophie, don't you think you've asked and answered your own question there?
Do I have to do domain and range or not?
It doesn't ask you to do domain and range, but you do need to do the endpoints if you've been given a restriction. So Sophie asked, even though, I'm going to rephrase it ridiculously for you. Sophie asked, even though there are no x-intercepts, do I still have to calculate them? The answer is no. So when you know that the horizontal asymptote is the x-axis, then you can conclude quite rigorously that there are no x-intercepts, so you don't need to do them. But if the horizontal asymptote had changed, then you would have to calculate them if they were within that domain. Every single time you have a function and you are asked to work out the x and y intercepts, every single time, regardless of what graph you've been given, you do the same process. Substitute in. Okay, so y-intercept, oops, although it's not the y-intercept, is it? So we let c equal 0 and I'm sorry, were you talking to me or someone else? Oh, sorry, Ansel.
The last slide, you wrote y equals 0.
Oh, I'm sorry. Where did I do that? Thanks. So it's t equals 0.
It doesn't matter when you're doing work in keeping one. I do that sometimes.
So do I.
Yeah, absolutely matters. Yeah. Well, it's either laziness or a lack of being able to translate x and y to c and t. I mean, you can see from my perspective, I forget, but I correct myself. Yeah, pretty much. Yeah.
No, my they like just use y x and y. Like, why do they bother with like so many variants?
Can we leave that? I mean, I think it's like a nature of mathematical kind of discussion there. It's quite simple that as human beings, we tend to label things to help us understand what's going on. And although x and y speaks to maybe the math part of the brain, we've got axes, I can really only deal with x and y. Technically, the formula makes more sense to talk about C for Celsius and T for time. Sorry. Having said that, though, I look at it every time I see that word, that letter C, I keep on thinking of the speed of light because it's often used for that. So, you know, there is ambiguity everywhere, but the better we can sort of challenge that ambiguity, the better we are, I think. So t-intercept, let's C equals 0. T is equal to 1,000 over 0.6 multiplied by 0 plus 331, which equals, to cut a long story short, what do we expect it to be? Roughly, that is exactly what it is, but roughly that would be what? Roughly 3, wouldn't it? 3.02. So it'd be roughly 3, wouldn't it? Because we've got 1,000, we're dividing it by roughly 300. Have I spoken to you before about the fact that in the IB they expect you to round things to 3 significant figures if you're going to do any rounding? Doesn't matter. But I was always going to mention it.
Yeah, true. Wait, so
Yeah.
even if the question only, even if the least, like even if the value of the least significant figures is only like 1 or 2, you still round to 3. No, you round up to the least one unless you have like a dozen zeros, and then you round to 3. 3 is the maximum. 3 is the maximum.
3 is the maximum. Yep. No, 3 is what you should round to if you're going to round at all.
No, but he's asking if it's like if
You're
you've
gonna
got,
have
if you've got 1
2.1.
significant figure plus 2 significant figures, you round to 2 significant figures if you need to. But you wouldn't then expand and make it complicated if your values aren't.
Don't you round to the fewest?
Exactly, yes. But 3 significant is the maximum.
So even with whole numbers, they expect that if you're going to round it, you would round it to 6,430. Okay? But my general advice is, unless it explicitly tells you to round it, you should write it in exact values as much as you can. And it's absolutely true that they will ping you if you round too early. So if you round to 3 significant figures in the first line, and then you keep on calculating using the roundings, and then your answer is wrong as a result, they will ping you all the way through for that. Yeah.
More than I'm gonna go too early, or everything will be wrong.
No, we don't. Yeah, so you want to email me, okay? And then I'll do something about it.
Maybe we could do, search. I think we did search too early and made it extended. I wish we did another unit.
Sure. Anything you think you need a bit more practice around, make sure you email me. Okay, so this is the point, 0, 3.02. The other critical points, so we know there are no x-intercepts by inspection. That's how you say it. By inspection, there are no x-intercepts. I'm not going to write that down. But the other critical points are the endpoints. And so we have, it says here we need to sketch from -20 to 40. So when C equals -20, what do we have? This.
And why do you see
C for Celsius. Yeah, that's the thing I was saying before. The thing I was just saying. Actually, that's not like you. Okay, so 0.6 times -20 plus 331 I'm doing on my calculator. I get 3.13 to 3 significant places. So you see what I'm doing? I'm just substituting the points in. And just to keep it on the one slide, I'm just going to put it next to it, although that's bad manners, but I'm going to do it anyway. C equals 40. Yeah.
What is that V?
So, sorry, how do you know by
Probably me just squishing. Where's the V?
0.6 V. Oh, is that a times?
Times.
Oh,
That V there?
yeah.
Picky.
Sorry, no, I actually didn't know. I thought it was like another variable and I got really confused.
Is that better?
Yes.
you know by inspection that there's no x-intercepts because you can see that they're both asymptotes.
Because the x-axis is the asymptote. So it, by definition, cannot cut through. Okay, so now we've got 1,000 divided by, so I'm just using my calculator to work this out, 0.6 times 40. plus 331, close brackets, and I get 2.82 to three significant figures.
Wait, C plus 40. Oh, what? Hang on. What is the negative 20 and the 40 now?
So I don't have the question written into this presentation, but the question explicitly says for 3A, sketch the graph of temperatures from negative 20 degrees Celsius to 40 degrees Celsius.
Oh, okay.
So negative 20 and 40 are what we call the endpoints of the domain. And so I've substituted in the endpoints to see where they would be. Yeah. And you can see I've got 3.13 over on the left at negative 20 and 2.82 over on the right. And I know that in between them is 3.02 because that's the t-intercept. That sounds good to me. It's going down ways. There's a 3.202 in the middle. That all seems to be right. So technically, and I'm just going to just take Jeremy's suggestion and just do a bit of a zoom up here. So over on the slide on the left, sorry. Was that a rhetorical question? Nothing. So I'm going to write negative 20 here. Now my graph is not to scale. The axes will be scaled roughly, but they're not scaled in proportion to each other. So it's cutting through, sorry if I'm zooming in and out, I just want to get it right, at 3.02. So I've got something like this happening. Like that. This is 3.02. So notice how I did the graph first and then put my points in. This is negative 20 and 3.13. And this is 40 and 2.82. And I'll now zoom out so you can see it all in glorious Technicolor. Yeah, I really, really don't. It is the same graph, it's zoomed out. Jeremy really wants me to do a zoomy thing, but I just don't have the emotional energy to do that.
Oh, wait, I can't read the...
Oh, yes, Richard.
Is that better? A little bit better?
You're halfway there.
Is it better? Sorry? Guys, I can't hear Sophie. Zoom in. Okay. So technically, just to emphasize that with 3A, technically, I could have just drawn the bit in the purple box there, right? That's all I was asked to do. But by drawing the full graph, not only did we get to practice just drawing a rational graph anyway, which doesn't hurt, it also gave us an idea about why the answer looks like it does in the back of the textbook. And that to me is pretty useful to know. So there. Okay. And that was the 10 minutes that I allocated to reviewing our homework, which is now 40 minutes in. Sorry?
40?
Yeah, it's 20 past 2. Yes, we did. I'm not going to do it because I really need to move on, Sophie, but I'll just say, it says here, if you're 1 kilometre away and it's 3 seconds before you hear the thunder, what's the temperature? So... So the formula is the time taken to travel 1 kilometre. It's not too hard. It's actually pretty easy. You've been given the number of seconds, which is 3. So you would replace T with 3, and then you would solve for C. Okay, I just don't want to spend, it would take me a little while to do it, but it's not hard. It's a bit long, but it's not hard. You multiply both sides by the denominator, 0.63 plus 331, and then keep going from there. Okay, that's the general approach. Sophie, it's okay. Okay, theory notes. I can't wait for you guys to play this back so that you can sort of see how random you are.
It's the one. I know how bad that microphone is.
That was Zoe, just in case anyone's.
Yeah, Zoe took a lot of testosterone pills as well. I know that microphone can't pick up anything with outside of that.
It's actually that it's too good in that it's got sound isolation going, so that phone calls are really clear.
You can stop flexing on a
Oh no, I don't need to. It's just that it's actually not because it's too weak. It's because the technology is too good.
I love it.
That's what I'm going to put on my gravestone anyway. Not that I'm too weak, it's that my technology is too good.
I'm gonna add iPad Pros to my plan. They're so good. They're so cool. I just do my uni stuff.
I'm writing stuff.
Okay, so these can be summary notes.
Summary notes. But I'm gonna talk to you about it.
Yeah, she's not behaving rationally. She's also to be free. Yes. Also to be free.
Okay. You do you, boo. But also,
Okay, so this is different to. No, it isn't.
wow, look at that beautiful hair.
Oh,
The rest of the word just kind of deteriorates, right?
That's clearly.
No, it is not. Who's that?
Look at that hole here.
I'm just going to keep on writing, guys, because you clearly don't need me to be talking through.
Isn't it over GX and then plus K at the end, or plus something else?
Oh, thank you. You can see it. Yeah. I have my eyes. Yeah. That's nice. That's what it is. You know what?
And this has X on the top and the bottom.
Fingers off. There's one of my friends that they got my fingers off.
I knew about blue that fingers off the shop.
I'm sorry that no, it's bad. I know it's really difficult.
I've got most of that.
Of course you do, because you can do that. Realize you've got one more class. Oh, I know, that makes me cry. No. Are you? I doubt it.
That's not it. other shape is called? An asymptotic hyperbola.
What does that say? A hyperbola. Just,
Yes.
what is the asymptotic?
It's got an asymptote.
Wait, what's a hyperbola? Can I just say it wrong?
Yes.
Yeah, I know. What is it?
The fact that it has asymptotes means it's
What's the other thing?
hyperbola is that shape.
Hyperbola.
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 Oh, yeah. Do I just think of like,
Yeah, no, it's
Actually, I'm kind of glad it's on the English. Don't have to concentrate so much.
We have an in-class essay, so yeah.
You're gonna do great. Believe in yourself. Oh, wait, so f of x over g.
Right, I need to talk to you about it now, and I'm glad you've finally fallen silent. So, the general function that we're going to be considering, the general rational function, is just like ax plus b over cx plus d. So, two linear functions, right? So, if we look at the rational function and we look at as x approaches infinity or negative infinity, so in other words, as regardless of sign, x gets massive, right? As x gets massive, the plus b and the plus d are meaningless, right? Even if you had 3x plus 1,000 and 2x plus 1,000,000, if x is like 1,000,000,000 trillion, then the 1,000 and the 1,000,000 are still pretty negligible in the grand scheme of things, right? So what we do is we say we can kind of ignore the b and the d. Yeah? The b and the d are meaningless. And so the vertical asymptote really focuses around the ax and the cx, right? As x gets really, really large. Now, if we've got ax over cx as x gets really, really, really large, then the x would cancel out. Looking at me because so you can't see it, not me at the screen. So the x would so the b and d is meaningless. The x cancel out top and bottom. So that means we end up with the vertical asymptote simply being a over c. So I want to try and capture that very briefly.
So G and H, do they have names? So are they?
They're just functions, just any two functions.
So a reciprocal function is just a different version of that general.
The reciprocal function is where g of x equals 1.
I mean, I've written that, and I've done
Or
g on the reciprocal.
G of x equals a. Yeah. So the reciprocal function is a specific interpretation of a rational function.
Multiple questions. First of all, why is B and D negligible if we put them in there?
Why is b and d insignificant?
Yeah.
Oh, okay. So don't write this down, but I'm just going to draw it for you. So if I have y equals 3x plus 2 over y equals 2x plus 1, okay, they're important, aren't they? The 2 and the 1 in the context of this. But if I now consider the behavior of the function when x is really big, okay, so it approaches infinity, like that's what the vertical asymptote does though, right? It looks at what's happening to the graph as x gets big. That's what the vertical asymptote does, all right? So as x gets really, really big, like 1 trillion, then I'd have 3, think 1, 2, 3, plus 2 over 2. 1, 2, 3, 1, 2, 3, 1, 2, 3, 2, 3. Oops, there's something dodgy there. Plus 1. So when x is big, this plus 2 and this plus 1 don't really change the value of the function. And that's just a trillion. Imagine if it was like a googolplex, a really big number. So as x gets huge, then the function tends towards just this part of the graph, right? And if we then just look at this part of the graph, and I'm going to go over to slide 6 now, slide 7, then if the graph tends towards this kind of pair here as being the most significant part, then it means it must tend towards A over C. So that becomes the vertical asymptote. Am I making sense?
Yes.
Awesome. Except,
That makes
no, that's right, yep.
Wait, so B and D is only negligible when X is bigger or smaller?
Well, I'm really just I'm cutting a few corners when I say that. What we're trying to do is that we're trying to drag this function to infinity. And when we drag the function to infinity, we're asking ourselves, what value is the function tending towards? And as we make x larger and larger and larger, it's tending towards A over C as the y value, sorry. So it's not actually the value. It's not actually that 1 and 2 is insignificant, but it's really just looking at the shape of it. The horizontal asymptote, I've got them around the wrong way. I'm so sorry. That's the horizontal asymptote. So sorry. Because I'm talking about as x increases, what's y going towards? I'm so sorry.
What was the term you used? It was a specific
Version, will do. So that's the horizontal asymptote. I'm so sorry. And the vertical asymptote. So from our homework, and this is why I sort of spent some time on it, I'm hoping you got a strong feeling that the vertical asymptote is what is happening when it's affected by when the denominator is equal to 0. So I'm going to write that in. So it's negative D over C. I would never bother trying to memorize negative D over C. I would instead encourage you just to think very carefully about what's happening. Set the denominator equal to 0 is the takeaway message. In the case of the general function, it would be negative D over C, but please don't try to memorize that. Memorize that first point there. In fact, I'm going to highlight it. That's how excited I am by that.
Wait, so negative DOC is wrong or
no, it's right, but it's a bit meaningless. Whereas if you remember that you set the denominator equal to 0 and solve, you should be okay. If that kind of makes sense. That's what you're doing. Okay, I'm going to go through an example. And that'll basically take us to the end of the lesson, unfortunately.
yes, I think, yeah, I'm going to do that. We're going to bleach, and then maybe I can get like some random wash out and dye. Yeah, I don't know. I'm feeling a bit fancy. I'm feeling a bit fancy too. I think I'm going to go pink next time. Oh, wow.
Okay, it is just send you home. It is a linear function over a linear function. It's a rational function. And we just go through our usual process for graphs, and that is we work out the vertical asymptote, the horizontal asymptote, we work out any intercepts if they exist, and go from there. Okay, so let's go vertical asymptote first. So V dot A dot for vertical asymptote. So we go 6x minus 12 is equal to 0, 6x is equal to 12, and x is equal to 2. We okay, Sophie?
Yes.
Easy as that. Now, I'm just going to maybe just draw the graph over in the next slide so we can sort of see what's happening as I build it up a bit. I can't remember what this graph is going to look like, so I'm just going to try and keep it fairly centered. So we've got y and x, and I've just worked out that the vertical asymptote is x equals 2. So I'll just draw that in. Is it positive 2? Yep. I'm hoping that this is going to be a decent scale here. Okay, so that's x equals 2. Horizontal asymptote, y is equal to 3 on 6, just like that, a over c, which equals a half. So now I'm going to put my horizontal asymptote in. So if that's 2, half would be about here. Okay, so that's y is equal to a half. Good so far? Yeah. Okay, I can see that my graph is going to have a y-intercept and an x-intercept, so I'm going to have to work those out just by inspection. Is that okay? That's going to have because we know what the graph shape's going to look like. So I'm going down to slide 11 here. So y-intercept is let x equals 0. So I'll have y is equal to 3 times 0 minus 2 over 6 times 0 minus 12. So that's equal to negative 2 over negative 12, which is equal to 1/6. So that's 0,16. And I'll just do it next to it here. The x-intercept is where y is equal to 0. And so I'll have 0 is equal to 3x minus 2 over 6x minus 12. Now I can multiply both sides by 6x minus 12. That's fine in this context. So I end up with 0 times anything is just 0. So I end up with just 3x minus 2 on the right. And then I can solve that. So my y-intercept is 2/3, 0. Okay, pretty small numbers there, unfortunately, but there's not much I can do about it.
Hang on, why is it 0 equal to 3x minus 2?
Because I multiplied both sides by 6x minus 12, which eliminated it. That left me with 3x minus 2 all by itself on the right, and just 0 on the left, because 0 times that is just 0. And then I added 2, divide by 3. You can do it as long as you rule out the impossible value for x, which would be 2.
Oh, see, I've always wondered if you can multiply the denominator by 0 and that works. But that is actually
you're multiplying the denominator by itself to get rid of it.
Yeah, but on the other side you can multiply by
Yeah, as long as x doesn't equal 2.
Okay, sweet.
Yes, I will, but I just haven't quite finished. I know it's time, Sophie, but I've just got another minute. So the important thing, the reason why we need to do this, even though it's going to be hard to graph, is what this tells me is that the y-intercept and the x-intercept are positive, right? It means that it's not going to do this. I'm going to do it and then rub it out. It's not going to do this. Oops, that's stupid. Right? It's not going to go through the x-axis. Sorry, it's through the origin. It's not going to do this, as in cut through here and here. I know that it's going to cut through here and here. That's what working out the intercepts tells me. So I can now graph it with more confidence, I might just actually graph it in red so it stands out from the asymptotes. So it's going to be something along the lines of, I found out the reason why I find it difficult to graph, more difficult to graph on the screen, is because the screen creates drag with my hand. Yeah, so I can't quite get a smooth run at it. And then I know because I know it's a hyperbola in shape, I know that the other side's going to be like that. And then I'll just simply grab my blue pen and go, that's equal to 1/6. And I know this, part is 2/3, 0. Again, I haven't done a great job with that, but it certainly does give a certain sense of the graph. Does the trick. Tomorrow, we will start. Everyone know this. When you walk into the room, I want you to start by doing exercise 5D, question 2. It's going to be on Google Classroom. See you tomorrow. My ear's hot. I think this made my ear hot. Am I sharing too much?